Welcome to our journey through engineering mechanics, a foundational subject for anyone pursuing engineering or applied sciences. In this video, we'll explore the core principles that govern how forces interact with objects, focusing especially on the concept of moments. Whether you're a student preparing for exams or simply curious about how structures and machines work, this series will break down complex ideas into clear, manageable steps. Let's start by understanding what engineering mechanics is and why it's so essential in real-world applications, from bridges to machinery. Engineering mechanics, often coded as EN.FRANCIS 2143, is a key course offered by the Faculty of Engineering Sciences and Technology. The curriculum covers a wide range of topics, including units and dimensions, laws of mechanics, vectors, forces, moments, equilibrium, and properties of surfaces and solids. Throughout this course, you'll learn to analyze and solve problems involving forces and their effects on bodies, both at rest and in motion. This knowledge forms the backbone for advanced studies in structural analysis, machine design, and more. Let's briefly outline the main topics you'll encounter. We start with the basics, units and dimensions, and the fundamental laws of mechanics. Next, we dive into vectors and how they represent forces. You'll learn about equilibrium both in 2 and 3 dimensions and how to draw free body diagrams. We'll also cover properties of surfaces and solids, including centroids and moments of inertia. Each topic builds on the last, creating a comprehensive understanding of how forces and moments shape the world around us. One of the most important concepts in engineering mechanics is the moment. The moment of a force measures its ability to rotate an object around a fixed point or axis. This is crucial in understanding how levers, beams, and other structures respond to applied forces. Moments are everywhere, from opening a door to using a wrench. In this section, we'll break down what moments are, how they're calculated, and why they matter in both static and dynamic systems. Moment is defined as the product of a force and the perpendicular distance from the point or axis to the line of action of the force. The formula is straightforward. Moment equals force times distance. The unit of moment is Newton meter nm. Moments can act in either a clockwise or counterclockwise direction depending on the orientation of the force. Understanding the sense of a moment is essential for analyzing the stability and equilibrium of structure. While torque and moment are closely related, they are used in different contexts. Torque typically refers to the turning effect in rotating objects, such as wheels or motors, and is associated with motion. Moment, on the other hand, is often used in static cases, such as analyzing beams or structures where forces act but no movement occurs. Both are vectors and calculated using the same formula, but the distinction helps clarify their applications in engineering problems. Calculate the magnitude of a moment. Simply multiply the force applied by the length of the lever arm. For example, if a force of 10 newtons is applied at a distance of 2 meters from a pivot, the moment is 20 nm. If multiple forces are acting, the overall moment is the difference between the total clockwise and total anticlockwise moments. When an object is in equilibrium, the sum of clockwise moments equals the sum of anticlockwise moments. Moments can act in either a clockwise or anticlockwise direction. The direction is determined by the way the force tends to rotate the object. In diagrams, a curved arrow is often used to indicate the sense of the moment. Clockwise moments are usually represented by, while anticlockwise moments use. This distinction is important when summing moments to check for equilibrium in structures. Sense or direction of a moment can be determined using the right-hand rule. Point your thumb in the direction of the axis and curl your fingers in the direction of the force. The way your fingers curl shows the direction of rotation. This rule is especially useful when dealing with three-dimensional problems or when visualizing the effect of forces in space. When multiple forces act about a point, their combined effect is called the resultant moment. This is the single moment that has the same rotational effect as all the individual moments combined. To find the resultant moment, sum all the clockwise moments and subtract the sum of anticlockwise moments. If the object is balanced, the resultant moment will be 0, indicating equilibrium. Let's look at a basic example. Suppose a force of 100 N acts at a distance of 2 m from a pivot point O. The moment about O is calculated as 100 N times 2 m equals 200 Nm, acting in the clockwise direction. By extending the line of action and identifying the moment arm, you can visualize the tendency of the force to rotate the object. This approach is fundamental in solving more complex problems. When a force acts at an angle, only the perpendicular component contributes to the moment. For instance, if a 40 N force acts at a 30-degree angle at a distance of 4 m, the moment is calculated as 40 N times 4 m times cos 30 degrees. This gives a moment of approximately 229 Nm. Always resolve forces into perpendicular components when calculating moments in such cases. Let's consider a force that creates a counterclockwise moment. If a 60 N force acts at a distance of 1 m at a 45-degree angle, the moment is 60 N times 1 m times sin, 45 degrees, which equals about 42.4 Nm in the counterclockwise direction. Identifying the direction of the moment is crucial for correctly summing moments in equilibrium problems. For an object to be in equilibrium, the sum of all clockwise moments must equal the sum of all anticlockwise moments. This principle is used extensively in structural analysis and design. By setting up equations based on this condition, you can solve for unknown forces, distances, or weights in a variety of engineering problems. Imagine a uniform rod OB, 10 meters long and weighing 6 kg, pivoted at point C, 4 meters from A. To keep the rod in equilibrium, a mass must be attached at A. By taking moments about C, we find that the required mass is 1.5 kg. This type of problem is common in engineering, where balancing forces and moments ensures stability and safety in structures. Consider a beam with weights attached at both ends and a pivot somewhere along its length. By taking moments about the pivot and setting the sum of clockwise and anticlockwise moments equal, you can solve for unknown distances or weights. This method is widely used in analyzing bridges, cranes, and other load-bearing structures. A uniform beam resting on two supports with masses placed at different points is a classic problem. By resolving forces vertically and taking moments about one support, you can calculate the reaction forces at both supports. This approach is essential for designing safe and efficient support systems in buildings and bridges. Non-uniform beams, the center of mass may not be at the midpoint. By placing weights at known distances and ensuring equilibrium, you can calculate the position of the center of mass. This is important in real-world applications where materials are not evenly distributed, such as in ships or aircraft. A rod suspended by two strings at different points creates a system where tensions in the strings can be found using moments and vertical force balance. By taking moments about one support and resolving forces, you can determine the tension in each string. This principle is used in designing suspension bridges and cranes. Footbridge modeled as a uniform beam with a child standing at a certain point is a practical example. By knowing the ratio of support forces and applying moments, you can find both the force at each support and the position of the child. This type of analysis ensures the safety and stability of pedestrian bridges. When a non-uniform rod rests on two supports and an additional weight is placed at one end, you can use moments to find unknowns like the center of mass or the weight itself. By setting up equations for different loading scenarios, you can solve for multiple variables, a technique widely used in structural engineering. Heavy steel rod attached to the ceiling by cables is a classic statics problem. By taking moments about the center and resolving vertical forces, you can calculate the tension in each cable and the weight of the rod. This analysis is crucial for designing safe lifting and suspension systems in construction and industry. When a log rests on two supports and forces are applied at the ends, you can analyze the point at which the log is about to tilt. By taking moments about the pivot point, you can estimate the weight of the log and how it changes if the log is non-uniform. This method is used in safety assessments for temporary structures. Force couple consists of two equal forces acting in opposite directions, separated by a perpendicular distance. The net force is zero, but the couple creates a turning effect or moment. Force couples are fundamental in understanding how wrenches, steering wheels, and other tools work. The moment of a couple is calculated as one force times the distance between the forces. Moment produced by a force couple is constant, regardless of the point about which it is calculated. This property makes force couples unique. They are considered free vectors, meaning their effect is the same anywhere on the body. The moment of a couple is simply the force multiplied by the perpendicular distance between the forces. Two couples are considered equivalent if they produce the same moment and lie in parallel planes with the same sense of rotation. This principle allows engineers to simplify complex systems by replacing multiple couples with a single equivalent couple, making analysis more manageable. Let's solve a couple moment problem. Suppose two 5N forces act in opposite directions, separated by 20 m. The couple moment is 5N times 20 m equals 100 Nm. If the forces are reversed, the moment changes sign but the magnitude remains the same. This calculation is essential in designing gears, levers, and rotating machinery. Force couples are used in engineering because their moment is independent of the axis or point about which it is calculated. This property simplifies the analysis of many mechanical systems. For example, the torque applied by a wrench is a force couple, and its effect is the same regardless of where you measure it on the bolt. Moments can be represented as vectors using the cross product. The moment of a force F about point O is given by MO equals R times F, where R is the position vector from O to the point of force application. This vector formulation is especially useful in three-dimensional problems, allowing you to calculate both the magnitude and direction of the moment. When forces and positions are expressed in Cartesian coordinates, the moment can be calculated using determinants. For example, if R and F are given in terms of I, J, and K components, you can expand the determinant to find the moment's components along each axis. This approach is powerful for analyzing complex structures in 3 dimensions. Suppose two forces act on a rod, and you need to find the resultant moment about a flange at point O by expressing the position and force vectors in Cartesian form and applying the cross product. You can calculate the moment as a vector. This method is widely used in mechanical and structural engineering to ensure stability and safety. Let's calculate the magnitude of a moment created by a 60N force directed from point C to B on a pole. By finding the unit vector from C to B, multiplying by the force magnitude, and applying the cross product with the position vector, you get the moment's components. The magnitude is then found using the Pythagorean theorem, giving a result of 224 Nm. Moments are a fundamental concept in engineering mechanics, helping us understand how forces cause objects to rotate. By mastering moments, you can analyze and design structures, machines, and systems with confidence. Remember to always consider both the magnitude and direction of moments and use vector methods for complex problems. Principles of moments are applied in countless real-world scenarios. From designing bridges and buildings to ensuring the safety of cranes and elevators, understanding moments is essential for engineers. Even everyday tools like wrenches and scissors rely on the concept of moments to function effectively. In tackling moment problems, always start by drawing a clear diagram and identifying all forces and distances. Use free body diagrams to visualize the system and carefully apply the right-hand rule to determine the direction of each moment. Double-check your units and ensure all distances are measured perpendicularly from the axis or point of rotation. Frequent error in moment calculations is using the wrong distance. Always use the perpendicular distance from the axis to the line of action of the force. Another mistake is neglecting the direction of moments, which can lead to incorrect results. Practice setting up equilibrium equations carefully and double-check your work for accuracy. In advanced engineering problems, moments often occur in 3 dimensions. Using vector cross products and Cartesian coordinates allows you to analyze these situations accurately. This approach is essential for designing complex machinery, vehicles, and structures that operate in all directions. Let's review the key formulas. Moment equals force times distance perpendicular, and for couples, moment equals force times distance between forces. In vector form, moment equals r times f for equilibrium. Sum of clockwise moments equals sum of anticlockwise moments. Mastering these formulas is crucial for solving a wide range of engineering problems. Try solving a problem where a beam is loaded with weights at different points and supported at both ends. Draw the free body diagram, set up the equilibrium equations, and calculate the reaction forces at each support. Practicing these problems will strengthen your understanding and problem-solving skills. Consider a scenario where 2 equal and opposite forces act on a bar, separated by a distance. Calculate the moment produced by the couple and discuss how the result remains the same regardless of the axis chosen. This reinforces the concept of couples as free vectors in engineering mechanics. Work through a problem where forces and positions are given in vector form. Use the cross product to find the moment about a specified point. This exercise will help you become comfortable with vector operations and 3-dimensional analysis. Bridge design, engineers use moments to ensure that the structure can safely support loads from vehicles, wind, and its own weight. By analyzing moments at various points, they determine the size and placement of supports, beams, and cables. This ensures the bridge remains stable and secure under all expected conditions. Moments are also critical in machinery such as engines and gear systems. Proper calculation of moments ensures that components rotate smoothly and efficiently, preventing mechanical failure. Understanding moments helps engineers design safer and more reliable machines. To sum up, moments are a cornerstone of engineering mechanics. They explain how forces cause rotation and are essential for analyzing and designing structures and machines. By mastering the calculation and application of moments, you'll be well equipped to tackle a wide range of engineering challenges. Now that you have a solid understanding of moments, you're ready to explore more advanced topics in engineering mechanics, such as centroids, moments of inertia, and dynamic systems. Keep practicing and remember that a strong foundation in these principles will serve you well throughout your engineering studies and career.